Giuseppe Habib received his PhD in mechanical engineering from Sapienza University of Rome, Italy, and the Budapest University of Technology and Economics in Hungary in 2013 as part of collaboration between the two universities. So after he completing his PhD, he spent 3 years as a postdoc researcher at University of Leek, Belgium.
Yes.
And he later returned to Budapest as part of Marie Curie postdoc fellowship. He is now an associate professor at the Department of Applied Mechanics at Budapest University of Technology and Economics and head of Global Dynamics Research Group, where he has remained since 2016. So basically, Budapest University of Technology and Economics is the best university in Hungary, and also it's world-leading institute in mechanics, actually. So it's top university in mechanics. And his research interests include nonlinear dynamics with a focus on global dynamics, dynamical integrity, vibration mitigation, and nonlinear dynamic vibration absorbers. And I think he is really a rising star in this field on nonlinear dynamics, and also a real expert who really developed something new and something useful for both academy and the industry. So I think we as civil engineering people, we will learn a lot from his presentation. So now, Giuseppe, the stage is yours.
Thank you very much, Silly, for the introduction. It's really a pleasure to give this lecture. I'm sorry I cannot be there in person. I would love to be there in person, hopefully next time. So I really want to visit Shanghai and your university, definitely. So first of all, let me introduce my collaborators, which are Bence Sachs, Dora Patko, Fanny Kader, Balazs Bauer, and Martin Sabor, who all contributed in some parts to this to the work I'm going to present. And then let me okay. So let me say something about the Budapest. Budapest is in Hungary, which is in Central Europe. Budapest is a city on the Danube River, which really characterizes the city. It's a very beautiful place, actually. It's very interesting to visit. I really suggest anyone who has the possibility to visit it. We have actually a very large Chinese community as well. It's a very nice place, actually. So I really invite you to come. You're always welcome. If anyone is interested in coming for a short visit, like scientific visit, for any collaboration, we're really open and enjoy collaboration. So anytime, just contact me. I belong to the Department of Applied Mechanics, where we deal with several research topics. Like the main topics are vibration control, nonlinear dynamics, continuum mechanics, multi-body system, time-delay system, machine to vibration, also human balance and rolling body dynamics. These are the main topics, let's say. But about this presentation, I divided in two parts. First, I will talk about dynamical integrity estimation, and especially about the method that we developed, and then about some data-driven dynamics predictions, so data-driven techniques for predicting the dynamic of the system. But the particularity is that we use a minimal amount of data, so like a single time series, and from that we try to extrapolate information. We don't need a lot of time series as typically data-driven system do. Okay, but let's start with dynamic integrity estimation, and I will start with a motivating example. So it's starting. Yeah. So here you see a truck on the highway in the United States, and the car with a trailer on the back is passing it. And you see, after it passed it, for the wind gust it got while it passed the car, vibrations are triggered, and the trailer starts to oscillate right and left very strongly until we have an accident. So it's flipped completely, the car and the trailer. And luckily, there was no serious injury in this accident, but it's a very common type of accident that can happen. So if you have a too large trailer, this is something that can happen. In this case, it was triggered by the push, by the wind gust that you get, when you pass a large truck in a highway, I think everyone experienced the wind that you get at the moment you are passing, and that triggers this vibration. So if you want to study this kind of problem, we can build a reduced model. So I was lucky to have prepared experimental setup for something like that. And so here we have a wheel which is on a trading mill, and this wheel can rotate in the yaw direction. Okay, so it's basically it's 1 degrees of freedom of the system, but we also have the flexibility of the wheel, so it's a more complicated system. And we can study, for example, the stability of the system in the velocity, the space, and the mechanic trail. Okay, for example, mechanic trail is this distance, basically, roughly speaking. And then we can try for this different value and see if the system is stable. For example, in this case, we see the system looks stable because if you give a perturbation, the system goes back to the original state. So we can put a green X here. We say, okay, system is stable. And but let's take a better look. So we have a small perturbation, and it's okay, no problem. Another small perturbation is okay, but if you give a large perturbation, the system starts to oscillate, and these vibrations are not dumped out; they stay there. So it doesn't really look stable in some other sense. Okay, so what can we do here? What's going on here? Is it stable or unstable? Should we put an X, green X, or a red circle here in our table? Now let's see what's going on in mathematical sense. So if you have a linear system, and here I'm presenting the phase space. So here we have the position, and here we have the velocity of the system. Okay, and here basically this represents the trajectory of the system, how position and velocity are changing in time. Okay, and the typical linear system can have one of the type of equilibrium that you can have is a stable focus. It means that the position and velocity are continually exchanging with each other. These are vibrations, basically. This rotation represents the mechanical vibration of the system, and they are damped until the system asymptotically reach the origin. Okay, and this is what happens for linear system. For nonlinear system, we can have similar scenario, but the difference is that I didn't mention it. Here we have only one solution. So only this equilibrium is the only solution that we have, and this can be stable or unstable. While in a linear system, we can have many solutions. For example, in this case, we can have a stable focus as the same one we had in the linear case, but also we have a periodic solution here, stable periodic solution, and we also have this unstable periodic solution. Okay, so we have three solutions which coexist. They exist for the same parameter value. And this is something that we don't have in linear system, but we can have in nonlinear systems. So basically, we have that the linear system is a representation of what happens for the nonlinear system only in this region. Okay, so basically, the linear system is a local approximation of a nonlinear system. This is something which is generic for man in general, can be said. And in nonlinear system, initial conditions are critical. In fact, if we start from, if you are in equilibrium here, and we make a small perturbation to the system, so we change position or velocity, for example, we go here, and then we'll start to oscillate a bit, and we go back to the original equilibrium. And while if you give a large perturbation to the system, so we increase position and velocity to a larger extent, for example, we go here into the phase space, then we'll not go back to the equilibrium, but we'll rotate and reach, have large vibration, which will reach this stable periodic solution, and it will stay there. So the fact that it's stable, it means that is a persistent state, that it can stand small perturbation. But as we see, this is stable, can sustain small perturbation, but not large perturbations. And this is exactly what happens in our example in the wheel, in the towed wheel. Where we have small perturbation, we went back to the origin. For large perturbation, we went to this large periodic solution. So what is the answer? The answer is that the system is stable, but it's not safe. Because in fact, from a mathematical sense, the equilibrium here is a stable condition, but it is not a safe condition, because if you have large perturbation, the system will start to oscillate. And for engineering, that's not a good behavior. So here I put a red cross to summarize this effect. Now, how can we study this kind of phenomenon? So there are several tools, but the most comprehensive tool are probably basins of attraction. So what are basins of attraction? Let's consider a relatively simple system. So we have a potential well where we have a particle moving in it. Okay, so this is a planar system. This is like, you can think about a ball which can move here around on this surface. Okay, so it's something that physical intuition help us to understand the system. And we have here three stable solutions. Okay, so these values are the stable solution. These are also equilibrium, but these are unstable equilibrium. Okay, so these are the three stable equilibrium that we have. Now the basin of attraction basically represent the system in the phase space. So here we have the position and here we have the velocity. And you see each, these three equilibrium correspond to these 3 points, which are the stable equilibrium that we have. And the color indicate to which equilibrium will end up. So for example, if we start from any orange point here, so for this position and this velocity, we are here in the orange region, we will end up to this orange solution, which is the solution on the right. The white region will lead to solution on the left, while the black region will lead to this other solution. Now we can think that this is our desired solution and these are undesired solution. Okay, so this is a state which is stable, but if you have a small perturbation, it's okay because the particle will oscillate and stop here eventually. But if you give a large perturbation, you will end up here. Okay, and this you can study through the basin of attraction because here it shows the amount of perturbation in terms of position and velocity. The problem is that basin of attraction can be very complex. For example, here we see if you have a similar system, we just give some harmonic excitation, and then this is the basin of attraction that we obtain. So it's fractal, it's very complicated, and it's hard to say something about it. It's one problem. And the other problem is how can this basin of attraction be computed? So there are a lot of methods, but actually for experimental system, it's almost impossible to obtain them. For the analytical methods, which are not so easy, are very hard to be implemented, and they are not generic. So in general, we can say that's not a general solution. It's not a solution only in some cases. Stochastic methods also have a lot of limitation. There are some numerical methods which are effective. For example, the cell mapping method. I don't want to go into the details of this method. This was developed more than 40 years ago. It's an excellent method. It's relatively fast. It allows parallel computation, but it's hard to implement, and there's memory issues for a large system. So that's the reason why, in my opinion, that's the reason why, even though it's a very effective method, in 40 years, still it's not used in engineering practice. It's only used for research purposes, but not in engineering. This motivates our work. So basically, the question we want to answer is, can we define the robustness of a solution without computing in basin of attraction? So we saw basin of attraction very hard to compute. We want to bypass this step and identify how much, for example, this solution is robust against external perturbation, and this is called dynamical integrity. It's called this property, the robustness against external perturbation. So without computing basin of attraction, directly identify the dynamical integrity. Okay, so that's the objective. And now let's see which part of the basin of attraction is really important. So here we see we have the fractal region. It's not really fractal here, it's just a very mixed region, but in some other cases fractal. In any way, this is not really useful for engineering purposes. I mean, if you are interested in the black areas, we don't want just to try to be lucky to end up on a black strip here, which will give us the desired solution. So that's not really useful in practice. And it's also hard to study this part. What is much more relevant is this region. This region here, the compact area of the basin of attraction. This is much easier to identify and is also practically very, very important. But we can do one step further to simplify our life and to do something which is even simpler to do. And we want to compute the so-called local integrity measure. Basically, the local integrity measure is the radius of the largest hypersphere, which is totally included in a basin of attraction, and it is centered in the solution. So basically, is this circle here. In this case, a two-dimensional system, and this is a circle. But you have to think that most of systems are not two-dimensional. Most of systems have large dimension. Even like a 3 degrees of freedom system already has dimension 6, okay? Because the dimension is position and velocity typically for mechanical systems. So the dimension very quickly can become large. And this is so it's not a circle, this is an hypersphere in general, okay? And so our objective really is to identify this hypersphere without computing basin of attraction, just focusing on this hypersphere. For this objective, we developed an algorithm, a toolbox, which so it's an algorithm which is now implemented in the MATLAB toolbox. You can download it. So here you can find it in my website, and I will be actually, if you are interested, if you have, there is a tutorial, but I will be very happy to help anyone who's interested in using it. So you can just email me, and I will be very happy to collaborate on any project which involves this toolbox. So I really want to make this useful for engineering. Okay, but let's describe how this toolbox works. So we have this algorithm work. The algorithm is very simple, actually. The idea is super simple. So what we assume first that we don't know anything about the basin of attraction. We just know our solution of interest. And then what we do, first thing, we define a phase space of interest. So we put some limit on the x and x dot coordinates. Okay, so we consider only one part of it. We don't consider all the. So we limit the phase space of interest. This can be physical limitation about the position and the velocity, for example. Then we perform a simulation. We choose a random initial condition, and we perform a simulation of the system. If you have a numerical model, mathematical model, this can be any kind of model. It can be a black box model, or it can be ordinary differential equation, anything, basically. Just we need to be able to obtain some trajectory. We obtain this trajectory, and this is a converging trajectory. So we verify if it converges or not, and we have an automatic method to do that. And if it converges, then we don't do much with it. We obtain another trajectory for another random initial condition. Now we see that this trajectory is not converging to the equilibrium, but is going somewhere else. It's going through another solution that we didn't even know about this solution initially. Okay, we assume we knew only about the equilibrium we're interested in. And now at this point, from this trajectory, we can already make a first overestimate of the local integrity measure. In fact, we know that this hypersphere cannot be larger than the minimal distance between our equilibrium and the diverging trajectory. So this is the maximum radius that we can have for our local integrity measure, and this gives our first overestimate. And then next step is that now we don't need to investigate all this space, but since we know this is the maximum size that we can have, we can restrict ourselves to study only what's happening here, and iteratively we can reduce this hypersphere to smaller and smaller dimension. Okay, so basically we repeat this procedure iteratively until stopping criterion is fulfilled. Now, although the algorithm is very simple, there are some issues. For example, automatic classification of time series, reduce computational time because we want to make something. So the idea is you want to make something fast that can be used by engineers, potentially also in industry. So that's the objective. So it must be fast and simple. So then we have to define distance in an anisotropic space because it's we have position, velocities, we could have temperature, we can have anything in the phase space. Then we have to choose initial condition of each trajectory in a smart way to have meaningful trajectories, and we need to define a stopping criterion. I don't want to go through all these steps because it's make too long the presentation and not so interesting. So I will just talk about time series classification. And if you have any question at the end, I'll be happy to answer. Okay, so for the time series classification, we exploit the subdivision of the phase space in cells. Okay, so we assume that the phase space is divided in cells, And then we mark the cell where is the desired solution. Okay, so we assume we mark this cell, this is the desired solution, and we mark this cell as a converging cell. And then we have our trajectory. Now, if you have a trajectory that reaches the cell where we have the desired solution, we stop the computation of this trajectory. We say that this trajectory is also converging. We assume that we have a converging trajectory. Well, if you have a trajectory that leaves the phase space, we assume that is a diverging trajectory. Actually, this trajectory could even come back. Maybe it leaves the phase space, then it re-enters it, and then eventually it could have reached this solution, the desired solution. But we assume these are physical constraint, physical limits that we don't want to pass. So if you have a trajectory which is going out of this limit, we assume its divergence is not valid for us. Then if you have a trajectory which has several points which remain in the same cell for like several, we fix a number, so above a certain number of points within the same cell, we assume that this trajectory converges to another equilibrium. Then if you have a trajectory which whose point pass through the same cell multiple times, not subsequent points, but pass through the same points, then we assume the trajectory reached the periodic solution. And then finally, if you have a trajectory which reaches any cell which was already tracked by a previous trajectory, then we assume that this trajectory has the same convergence properties of the trajectory that is reached. So, for example, this trajectory number 5 is convergent because it reached the cell, one of the cell of trajectory number 1, which is a convergent trajectory. Okay, so that's the logic. Now, the algorithm was applied on several systems. I will show some examples. So this is a very simple example, the Duffing oscillator. So we have this 1 degree of freedom system. It's basically something similar to the system we saw, I showed just for illustration before. We have two equilibrium here. And for this system, we could obtain the local integrity measure very quickly and precisely. And you see here with here as the iteration, with the subsequent iteration, the local integrity measure is rapidly converging towards the exact value. But this is a simple case. Anyway, it worked here. Now we tried to show some others. So this is a van der Pol Duffing oscillator with a vibration absorber. So I don't want to go into many details of the system. But basically, it's a two-mass system with a negative damping. So this damping is negative. So it makes this subsystem unstable because it's negative damping. It means something pumping energy into the system. But with this attachment, it can become stable. And in some condition, we have that this system has one stable equilibrium here, and it has a stable periodic solution around it. And in between, there is an unstable periodic solution. So it's similar to the case I showed before regarding the wheel. And also in this case, the algorithm worked very well, and quickly the local integrity measure converged to the correct result. But let me make a digression about Hopf bifurcations. Which is something very typical for nonlinear systems. So basically, if you have any dynamical system, it can lose stability at some point, changing one parameter. So here you assume that this is the amplitude of the system, amplitude of oscillation, for example, and this is a bifurcation parameter. Okay, so one bifurcation parameter means any parameter of the system. And then we have that until this value of the bifurcation parameter, we have that the equilibrium is stable. Okay, but then after this value, the equilibrium becomes unstable, so it will not be attractive anymore. If you have small perturbation, it will go away. Okay, because it's unstable. Now at this loss of stability, we have a so-called Hopf bifurcation, which means that we have a generation, we generate a branch of periodic solutions, which can be either stable or unstable. But we have this branch of periodic solution generated at the loss of stability. Now we can have two different scenarios of Hopf bifurcation. This scenario is a supercritical bifurcation scenario, when we have that this periodic solution is stable and is coexist with the unstable equilibrium. So we have here, we have in this region, we have unstable equilibrium and we have a stable periodic solution. Okay, while in this region we only have the stable equilibrium. While the other scenario, which is more tricky, is the subcritical bifurcation scenario, where we have still the same loss of stability. So if you see only the equilibrium doesn't change anything. We have here stable and then unstable equilibrium, but the branch of periodic solution is unstable and coexist with the stable equilibrium. Okay, so this means that if you have a supercritical scenario, then we have, if we are here for this parameter value, and this parameter can be, I don't know, can be if you are in, for example, in a flutter example, it can be a wing flutter or it can be a bridge. We have that this can be the wind, for example, and then here we have below a certain value of the wind, we have that the system is stable. So if you have, so the bridge will not oscillate. If you have perturbation, we'll have just small oscillation and we go back to the original state. While here we have for this wind speed, for example, we have that the equilibrium is unstable. It means that it will start oscillating. Whatever is even an infinitesimal vibration will cause the system to reach this periodic state, and we have large oscillation of the system. The problem with the subcritical scenario is that in the region where we have stable conditions, so here the system, the equilibrium is stable, we are below the critical wind speed, for example. If you have a small perturbation, no problem, the system will go back to the equilibrium. But if you have a large perturbation, which pass somehow this unstable periodic solution, it will lead to large oscillation. And the tricky part is that this can happen in the stable region. Okay, so if you study only linear stability, you will be tricked because you think here is safe, but here is not safe because you can have large perturbation, which will lead to large vibrations. So that's why it's tricky. So we can say that this is a stable but unsafe region, and this is a very dangerous case in practice. Typically, we have this branch of periodic solution then turns back, and we have another branch of a stable periodic solution. Okay, so it's limited the region of the dangerous region, let's say. Now, this is exactly what we have, the scenario that we have in the Van der Pol-Duffing oscillator with a vibration absorber. So we have this unstable Hall bifurcation. And we have a subcritical Hall bifurcation, which generate unstable periodic solutions and then periodic ones. And then this is the parameter range where we have the stability, and we can study here, we can apply here the local integrity measure algorithm, and we found this profile, which shows that if you are in this region, then local integrity measure is relatively high, so we have stability, but the system is safe, if you want. While if we move the parameter value, which can be, I call here negative damping, it can be the wind, for example, approaches the critical value. So we are not yet at the critical value, we are just approaching it. We see the local integrity measure decreases a lot. And this means that here, even though it's stable, it's very unsafe because small perturbation can be enough to pass this value and go to large periodic solution. Now here I see another example. This is more tricky. This is a pitch and plunge wing with a vibration absorber. It's more tricky, the bifurcation scenario that we have, because we have here again, this is an equilibrium, and this is a change, I call it wind speed. And here we have an equilibrium which is stable, and here it becomes unstable. We have a supercritical Hall bifurcation, which looks good in some sense. So we have this branch of periodic solution but then this branch turns back and goes back to the region where we have stable solutions. So we have basically, this region is very risky for us because here we have two solutions, and so also in this case only stability analysis is not enough. And if we study the local integrity measure, we found this profile of the local integrity measure, which confirm that what we see from this unstable solution, that here is the more risky point here. That is the unstable periodic solution is very low. It means it's almost touching the equilibrium. And this means that also the local integrity measure is low, and a small perturbation can be enough to pass this unstable solution and go to this large periodic attractor. Okay, maybe I will skip this example because I don't want to overload it with example. Okay, this is interesting because it's part of industrial collaboration. I cannot say many details because of secrecy, but we tried this algorithm on adaptive cruise control, and we found, in fact, some region which parameter value of the control gains where the system was stable but unsafe. So we have this adaptive cruise control. Even though it looks stable, it's stable, it could lead to vibrations if you have a too large perturbation. Then there's another case which is can be interesting because we have basin erosion basically. So it means that we have here we have periodic solution coexisting with chaotic solutions. So the system dynamics is very complicated, even though the system has only 1 degree of freedom. And I don't want to spend too much time on the details here, but we could measure it. For example, for increasing the force, we saw how the local integrity measure was decreasing, and this is called basin erosion. So basically, we had the chaotic solutions are eroding the basin of attraction of the periodic solution and making it not robust. We extended the algorithm also to time-delayed systems. So what is a time-delay system? The time-delay system is a system where the state of the system, the force applied on the system, does not depend only on the state itself, but also on the state in some previous time. Okay, and we have this effect, for example, in machining operation. If you write a mathematical model for machining, so this is a turning shutter, and we have this kind of time delay, which complicates the equation. The algorithm must be adapted to handle this time delay, but we work on that, and now it works. And here we can see. So here we have the colored part is the stable region. Okay, so this is a machining operation, and here we have the spindle speed. So spindle speed is the rotation of the tool, which is cutting, and here is the depth of cut. So how much material we are removing at each passage. And this is a very tricky thing to compute the stable region, but it can be done. And we have these lobes, stability lobes are called. So we have that in this region the system is stable, in this region the system is unstable, and we can have very large vibrations during the machining operation. What we were able to compute with our algorithm is that even though we have this is the stable region, if you have just a small change of the nonlinearity in the system, then the stable region that here is relatively stable, because here red color means that the local integrity measure is high. Changing the nonlinearity of the system, so a linear spring, this is a hardening spring, a softening spring. So if you have a hardening spring, in both cases, either hardening or softening spring, we see the local integrity measure is strongly reduced and the system becomes much less robust. And this type of analysis, so here we have to analyze many points on the map on this 2-parameter space. To make this analysis with other methods is practically impossible. It's computationally too expensive. Okay, we have some publications related to this code, and we have some others coming, working on some others. Again, the toolbox is available, and again, I would be very happy to collaborate on anyone interested on this. Then, if I have time, I'll move to the second part of the talk, which is about minimal data-driven dynamics prediction. And let's go back to the bifurcation scenario that I showed before. Okay, so here we have this half bifurcation. I will repeat again. So we have a stable equilibrium. Here is basically here we have a bifurcation parameter. It means parameter of the system that we are changing. Okay, and this is the amplitude maximum. If you want, this is the maximum amplitude of the steady state solution of the system. And here we have a stable equilibrium, which becomes unstable for this parameter value, where we have this bifurcation, and we have an unstable periodic solution. Okay, and this unstable branch of unstable periodic solutions turns back here, and here we have a generation of a branch of stable periodic solutions. Okay, so the same scenario that we have before, and I see that this scenario is actually relevant for a lot of real applications. So here I mentioned some, which is wheel shimmy, stick slip vibration, the time delay control, machining, fluttering stability, but also traffic jam dynamics, human balance. So a lot of diverse systems have a similar bifurcation diagram. And as I mentioned, we have here, before this so-called fold bifurcation, this fold point, the system is globally stable. So the equilibrium is globally stable. So any perturbation will lead to transient effect, and the system will go back to the equilibrium. Here is unstable, fully unstable, the equilibrium. So we will always reach this periodic solution. So this is a region where we don't want to be in any case. Let's assume that we want to be in equilibrium. We don't want to have vibrations. Okay, so this is where we are safe. Here is where we don't want to be, because we know that this is not good. And this is the tricky part, because it's stable. It's actually bistable, because we have two stable solutions, this one, and and it's unsafe. Okay, and a stability analysis will not tell you that this is bistable. Will only tell you that this is stable as this one. Will not make a difference between these two. Okay, and in this region here, we have this scenario. We have a stable equilibrium, stable periodic solution, and an unstable periodic solution in between. Now, the top bifurcation is easy to identify. If you have a mathematical model, typically this is just an analysis of the eigenvalues of a matrix, which is something easy. Or if you have experimental system, you increase the parameter, and then you will find that while you pass this parameter, the system is unstable, if you can make this kind of test. Okay, so it's something easy to identify. While to find its fold, it's much harder. Okay, and basically this goes to the first objective that we have with this minimal data-driven method, is that can we identify this fold only using the dynamic of the system before it. Okay, so we only use some transient dynamics that we have here in the globally stable region. We want to estimate if you are close to the fold, which mark the approaching of a region which is dangerous. Okay. Then the other objective that we have is about this unstable limit cycle. So as I showed you before, this unstable limit cycle is something which is really limiting the robustness of the equilibrium. Okay, so if we have knowledge of this unstable limit cycle, then we are one step ahead in terms of knowing how much is robust the system. And so it's a very useful information would be to know this unstable solution. It's not easy to identify this unstable solution, because if you just time integrate the system will reach stable solutions, will not reach unstable solutions. So it's not easy to find them. But our objective is to identify this unstable limit cycle only using transient dynamics around the equilibrium. So we are here at the equilibrium, we give a small perturbation, and we obtain something like this. So system converging at the equilibrium, and from this one we want to find the unstable solution. This is the second objective. So yeah, this is what we want to find. Now let's start with the first objective. This part is shorter than the first part, okay? So don't worry if it's taking a long time, but I'm close to the end. Okay, so let's see what happens when we have a fold at the fold that we want to identify. Okay, so this is our stable solution. This is a branch of stable periodic solution, and this is a branch of unstable periodic solution. Well, these are stable equilibria. Okay, and here we have a topological change between this region and this region. Now, before the fold, what we have that if you are far enough from the fold, we have the system in any case, even if you are close, the system will settle to the equilibrium, okay, because this is a globally stable region. While if you're after the fold, if you are in this region, the system, if we have a large perturbation, we start from large amplitude, the system will either reach the equilibrium from the top, or it will reach the equilibrium from the bottom if you have a small initial condition, or it can even go towards the equilibrium if you have a smaller initial condition. But now the question is, what happens near the fault? So because we have to pass between this dynamical scenario, this different dynamical scenario. So it's a very different scenario. So how is this transition happening? What is happening here? And then we see that here, basically, we have that the system is converging to the equilibrium because we are in the globally stable region, so it must converge to the equilibrium, but in a different way. So we don't have the classical exponential decay that we had before. Before we had some, if you take the peaks, we had some exponential decay like this. In this case, we have this sort of bump, okay? Now, this bump is actually the marker that we are approaching a fold bifurcation. And if we can identify this bump, then we can predict the fold bifurcation before founding it. So we can see that we are almost there. And with approaching the fold, basically this is how changes the shape of the time series that we have. Okay. And now we see that how can we capture this bump? How can we find this bump in practice? Now we saw that a good way to identify is using the logarithmic decrement. So here if you have a system which is behaving linear, we have the logarithm. What is the logarithmic decrement, I should say? Logarithmic decrement basically is given by this equation. Is the logarithm of the ratio between one peak and the subsequent peak. Okay. So if you have a linear system, this logarithmic decrement is constant. It doesn't change damping. This is a marker of the damping of the system. For a linear system, the damping is constant. It does not depend on the amplitude. And so we have that this logarithmic decrement will also be a constant line, which will not depend on the amplitude. While if you approach the fold, then we have the nonlinearity becomes more important. Then we see that this logarithmic decrement has some sort of value here. And then in correspondence of the bump, it becomes even more pronounced, this value of this decrement, this decreasing of the logarithmic decrement. And actually at the critical point, it will go to zero, this decrement. Now, we can exploit this to predict the fold. So we can take, for example, we take one time series for a parameter which is far away from the fold. And this is the logarithmic decrement group, the logarithmic decrement that we obtain. Now we can take this point and we can plot with respect to the bifurcation parameters. We have the minimum of the logarithmic decrement and we plot with respect to the bifurcation parameter. Then we move closer to the fold. So we approach the fold and you see this changed a bit. So here as it was and here as it became. And this point, the minimum gets lower. And if you plot this minimum with respect to the bifurcation parameter, now it's higher, the bifurcation parameter, we obtain this other point. We can go on and we obtain other points which are lower and lower. The minimum will be lower and lower. And finally, we see that so if you have enough points, then we can estimate the fold, because at the fold bifurcation, the logarithmic decrement will go to zero. And that's what happens. So at the fold, the logarithmic decrement goes to zero because the solution will not converge to the equilibrium, but it will converge to the periodic solution, not the zero equilibrium. And so we can use this to predict the fold, and we make some numerical trials, and it worked well. But we want to do the experimental thing to see if it's really something robust that can be used in practice. We applied on the rolling wheel system, and basically this is the bifurcation scenario that we obtain. We have that the equilibrium is stable until a given belt velocity, then it becomes unstable. And these are the periodic solutions that we have. So these are the stable periodic solution and that we could measure. This we couldn't measure, but you see that we have the periodic solution exists for a velocity which is lower than the critical velocity. So in this region here, between let's say 1.7 and 1.9, we have this B-stability. We have both periodic solution and equilibrium which are stable. And taking trajectories of the so perturbing the system for belt velocity below the critical one, we saw that the logarithmic decrement you can see. So this is the time series of the amplitude, and this is the logarithmic decrement. We could see the logarithmic decrement is decreasing, and if you are very close to the bifurcation, we don't have we have that this still goes to zero, but the logarithmic decrement during the decreasing of the amplitude is touches zero basically. And so if we plot this, so the minimum value of the logarithmic decrement with respect to the bifurcation parameter, which is the belt velocity, we see this decrement. And this can allow us to estimate that the default bifurcation will be here. So we can use this. Now, yeah, it's quite late. I don't know. Can I go on with this second slide?
Yes, sure.
5 more minutes? Okay.
No worries.
Okay.
No worries.
Thank you. Okay, so then I discussed about this unstable limit cycle estimation. So when we have this kind of bifurcation scenario, and now I don't really care about this high periodic solution. I just want to find this solution, because if we are above than this one, we will have large oscillation. This might mean an accident. Okay, so we don't want to pass this unstable solution. Now, so what do we have here? If you take this is the unstable solution. If you take a trajectory, this light blue line represents the trajectory. If we start trajectory very close to this unstable periodic solution, we see that this will, at the beginning, it will stay very close to it. Then slowly it will leave it, and then it will accelerate, and then it will approach the equilibrium. Okay, so this is what we have. And if we see this in time, the evolution of the x displacement in time, this is the profile that we obtain. Okay, so at the beginning is almost flat, it's decreasing a bit, but almost flat, and then it becomes much more steep, the decrement, and then we reach the zero asymptotically. Now, if also in this case we plot the logarithmic decrement, again, logarithmic decrement means the decrement of the ratio between one peak and the following peak. Since it's a ratio, since the logarithm of 1 is 0, okay? So here you see the ratio between these two peaks, which are very close to each other, is is almost 1. So the logarithm of this will be almost 0. And in fact, what we see here, the logarithmic decrement at high amplitude, so here is the high amplitude, we see the logarithmic decrement is almost 0. Then while we approach the equilibrium, we go on with the time, we see the curve becomes more steep. Steeper curve means that the ratio also becomes larger and the logarithm will be higher. And if the logarithmic decrement increase and reach then a value which is this value of the logarithmic decrement here reflect the linear damping of the system. But it's very interesting then that for higher amplitude it reaches 0. And basically this zero value, the logarithmic decrement, correspond exactly to the unstable periodic solution. So basically, if we can predict somehow this curve, then we can estimate the amplitude of the unstable limit cycle, unstable periodic solution. And now let's see what can we do with this. So we have our equilibrium, and now we take a perturbation which is not so large as before, so it's not starting close to the unstable solution, it's just a small perturbation, and the system is going back to the equilibrium. And this is the signal that we obtain in time, okay? So this is just transient vibrations. And if you see this with just with the naked eyes, you cannot really see that we have an unstable solution around it. So it's not visible. If you see just this signal, you think, okay, it's just a linear system with a stable equilibrium, nothing else. But then if you take this, the first 4 peaks, and I compute the logarithmic decrement, I obtain these 3 points. And then I can see that there's a clear decrement, decreasing of the logarithmic decrement. Now I made a quadratic interpolation of this, and I obtain a point where I expect that this curve that I presume is something like this is crossing 0. And I say that I can predict that at this amplitude we might have an unstable periodic solution. And I can say this only from this small signal which looks coming from a linear system, okay? But actually the system is non-linear, and the logarithmic decrement can highlight this information, okay? And we can use it to predict this unstable limit cycle. And then we can do, so now I did this on the peaks, but actually why should I limit myself to the peaks? So the peaks basically means velocity 0. So it's like a section here. It's like taking an intersection of this trajectory with a horizontal line here, okay? But I can do this also for any angle alpha here. So I can do for any line, like for any angle here. If I don't take the maximum, but I consider another way the coordinates. And then from each direction, I can estimate one point of the unstable limit cycle. And doing this, I can estimate the whole unstable limit cycle. And okay, this was done for a very simple system, but this is what I obtained. So the estimated limit cycle is basically overlapping perfectly the exact unstable limit cycle. Now, okay, the system was very simple. Actually, I didn't introduce the system, but let's do it on something a little bit more challenging. So this is a pitch plunge wing profile, 2 degrees of freedom system. We have this bifurcation scenario similar to the other one. Qualitatively, the system is similar, but there's 1 more degrees of freedom, and it represents some physical system. So it's not just a toy system. And in this case, I took this first red and black trajectory for my estimation. I didn't use the red part, I used only the black part, because at the beginning of the trajectory I have some sort of transient effect which is disturbing the estimation, so I had to neglect the first part. I took only the black part, and this is for the pitch degrees of freedom, this is for the plunge degrees of freedom, and in this dashed line represent the exact unstable limit cycle, while the estimated one is the green line. You see that even though I use something obtained from a small perturbation, the estimation is quite good. And from practical purposes, this can be a good indicator of how much you can go on with the perturbation before you reach, you might go to larger solutions and dangerous vibrations. We have 3 publications related to this work. But so I would be happy to discuss anything of this. If you are interested, you can just contact me. But to conclude, at the beginning, I show you an algorithm for estimating dynamical integrity, and the method is rapid. There's no memory issue, and the outcome looks meaningful from an engineering perspective. It has some limitation for the dimension of the system. It doesn't work with large dimensional system, but this method looks promising, let's say. Then I showed the method for predicting fault bifurcation is very easy to apply. It was experimentally validated. It does not need a mathematical model. And then finally, I showed the method to estimate unstable limit cycle, which is also easy to apply. It does not need the mathematical model. This was not experimentally validated, but we are working on that. So the moral of the story, nonlinear system has this multi-stability property, which is a sneaky property, is a problem. But if you use transient dynamic, we have a lot of information that can help us to handle it, to tackle it. And then I'd like to show you just what we see about visibility in the movies. So I'm not sure if you can hear the audio, but here you see a system which is not working, and then through some perturbation they are able to make the system work. So I'm not sure if you were able to hear the movie, but basically through perturbing the system they make the system work. And this is something that maybe everyone experienced when you have this vendor machine. You can take chocolate, and then you put a coin, and then the chocolate is stuck. It's not falling down. And that's a case where the system is bistable, because you have one good equilibrium state, which is down here, but the chocolate is stuck in another position, which is another equilibrium state, but it's not the desired one. You can perturb the system to make the chocolate go from the undesired state to the desired state. Then you see this guy, maybe he's expert about nonlinear dynamics, I'm not sure. He can apply a perturbation to make the system go as he likes. Okay, with this I conclude my presentation, and thank you for your attention.